All right. I was going to say one joke today, but I had an opportunity for two. This is actually a talk on Linux, and I am giving this presentation on a Windows laptop. I wonder why. It works fine on my personal laptop, so who knows? I don't know why the work laptop doesn't do mirror. All right. Actual joke I was going to tell. Who's ready for some assembly? Yeah, I know it's a little early in the morning, but don't worry. It's only one slide, 4 lines. Not a big deal. All right, so thanks for joining my talk today. We are going to be talking about Connect and why it's so slow through a case study at Cloudflare, which is where I work. My name is Frederick Lawler. I'm a systems engineer at Cloudflare, but publicly Linux engineer. Previously, I was a full stack developer, mostly focusing in backend web development. Just a little aside here, PHP developers make kernel developers. So these days, I am writing code for the Linux kernel and create tooling for various distributions for Linux. I primarily work in security and I dabble in networking performance. And today we are talking about networking performance in all its glory. Before we get started, who's familiar with Connect? All right, that's fine. We'll get into it. So, Connect is what's known as a system call, or as we like to call it, a syscall. Syscalls are your interface between user space and kernel space. When I say user space, I mean your user applications that you're running. So, in the previous presentation, we saw demonstrations of user space applications. All those applications interface with the kernel. So whenever you're making opening up a file, reading a file, writing to a file, those are all system calls. And today is no different when we're talking about sockets and the connect syscall and the bind syscall. So in a nutshell, this is how a browser works. We open up a socket. We tell it to use the TCP protocol. We make it connect to some website, in this case, Cloudflare's 1.1.1.1 at port 80, and we send an HTTP request to it, and notice how it is just plain text here. This is HTTP in a nutshell. You have whenever you create your services in say Java, PHP, what have you, Go, they're all going to have frameworks to build HTTP requests for you, but bare minimum, this is it. This is how browsers work. You create a buffer, in this case 4096, and print the data back once we get it. We're not going to be going into sending or receiving today. We are specifically talking about connect. So some terminology, I'll be using the terms egress and unicast. Egress is more simply known as we're going from one point to another in an outbound way. Ingress is the opposite. These are connections coming to you. So if you have a service on port 80, that's ingress. We're talking about egress. We're going out from our machines to something else. Unicast, one direction. So we're only going to a single destination. And this will become very important later. But for right now, just bear with me. We are making a single connect to one and only one location. We make 50,000 of them. So why do we do that? Cloudflare is known as a security company, internet company, cloud company, you name it, we do it. One of our products is CDN, where we distribute assets essentially all over the world, and it's a very unique way to quickly get an asset that's previously cached and brought back to you. So one day we were given a ticket about a performance problem within the actual cash flow pipeline. So in particular cases, when our customer, has an uncached resource, a user going to retrieve that resource will go through multiple layers of our cache throughout our network. But ultimately, since it's an uncached resource, we automatically go to your node, pull the asset, and then bring it back to the customer and then cache it. So the next person that comes in will have a quicker time retrieving that asset. So in our particular case, we had a customer that had an uncached resource, and we made 50,000 connections. So how do we do that? Well, by default on your Linux machines, if you run a sysctl, or other people might know it as a sysctl command, and you type in net IPv4 IP local port range, this will give you a complete list of the total ports you have available on your machine. So these are explicitly ephemeral ports that we'll be talking about today. And this allows us to make 56,512 connections based off this configuration to anywhere we want egress. Also ingress. This is important for ingress too, but we're talking about egress. So on normal systems, this number is a lot lower. You're not offered this many connections, but we specifically configured our nodes to, or servers, however you want to call them, to have this many ports available for us to use and exhaust. To do this, we also leverage a technique called bind before connect. So the crux of the problem here is we want the kernel to pick a port and connect, and to make this connection, make this egress connection for us, so we ourselves don't supply the port. And we'll get into more of that later. But for right now, we use this technique called bind before connect, which when we set this specific socket option, which is another syscall, and enable it, allows us to bind an IP address, a very specific source IP address, and then it tells the kernel to go ahead and pick a port for us. And then from there, we can say, all right, go ahead and connect out to the destination and the destination port. We have a really nice article, how to stop running out of ephemeral ports and start living long-lived connections, right here. I encourage you to read that later. So one fateful day, we saw a large spike. One of our customers in one of our, it looks like Dallas-Fort Worth, Texas nodes, had a very peculiar moment where we saw an upwards of 50,000 connections going out to an origin server. Now, normally this is fine, right? So when you, the customer, have are setting up your origins to deliver assets to be cached all around our network, ideally you have load balancing. Ideally you have all these other safety precautions put in place to be able to handle this sort of load. And Cloudflare is no different. We also handle this load too. We use two IPv4 addresses for this service. So for our caching service, what I mean is we kind of load balance between two IP addresses to be able to support this many outgoing connections. And here is a bimodal distribution of that. So the way these benchmarks were created was we used a tool called work, WRK, and its sole purpose is to generate load. And you can specify a duration, how many threads you want it to run on, yada, yada, yada. In this case, we set it to 48 threads. We set this to target a local IP address on basically my own machine, but it's really just some virtual machine out in the cloud. And we did this test for about 30 seconds. So for 70,000 connections. So we're trying to maintain 70,000 connections to this outgoing service, and this is the results of it. So we can kind of see that. I know it's a little difficult to read, but this is on the y-axis we have nanoseconds. On the x-axis we have the number of connections, and we can see that the vast majority of the connections are really, really fast. Lower nanoseconds, better, more fast, more fun. But then we can also see that we have a bimodal distribution where some of them are not quite as fast. So we wanted to take a little bit more look into that, because we don't want two IPv4 addresses, we just want one. So part of Cloudflare's initiative, we want to encourage IPv6. IPv4 is kind of going away. This is kind of the reason why. We want to use one IPv4 address, but we also want to know like what the performance impact of that is, because we can't just buy more. This information, like just in April of this year, per IP address, $50, and this is only for 250 of them. Can you imagine paying $12,000 for 250 IPv4 addresses? I sure can't. IPv6, way to go. But you know what? We all use IPv4, let's be honest. So performing the same benchmark test for one IPv4 address, we can see that now the vast majority of the connections are way, 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 way slow. And this is what our cache team was finding, and this is what we were trying to aim to fix. But just for funsies, what happens if we load balance over 3 IPv4 addresses? Everything's really, really fast. What's going on? So these are the questions that I'm going to answer today. Connect, why are you so slow? It's great for Cloudflare, but for, it's great for normal customers, but for Cloudflare, it's not all that good for us. We want to reduce our number of IPv4 addresses, but we also want the same performance as with one IP address. Short answer, we get there. So, time to investigate why this is the case. So we started off by taking a flame graph of a live production system. So this isn't representative of any of our synthetic tests so far, but this is an overview of what's happening on the system whenever somebody makes a connect syscall. We use a tool called func latency, which is a libbpf tool, which allows you to hook into basically any function you could ever possibly imagine, and then get the full stack trace, get full performance, whatever measuring of that function. And in this case, we're looking at a stack trace of the connect syscall. Now I know it's a little hard to see. I'll zoom it in here in a second, but the gist of it is that whenever we make a syscall, this is the exact call stack that we see. Anything in this fuchsia color, these are lock contention. So we can kind of see here, we can kind of get like a little bit of an idea here of like what our actual performance bottleneck is within this call stack. In case it's not obvious, we're gonna be focusing on inet hash connect, inet check established, and we're just going to ignore the spin locks because in our synthetic test, the spin locks aren't really an issue, and we'll find out why later. But these are the functions that we're going to try to focus on because these are the starting points into how we're going to determine what the performance problem is and how we're going to fix it. We're not going to be talking about IPv6 at all, even though it still runs through the exact same functions. They're just separated by basically branching statements, or as you guys might know them as if statements. But the general gist of this is when you tell the kernel to pick a port, it will pick a port. If you supply a port, it won't pick a port. It's that simple. So what's going to happen here is first it's going to try to get out and securely try to find a port, basically. Just generate a number, give me a port, what have you. We call that the port offset hash. We pass that into the inet hash connection, and based off that generated offset, we then do some randomness and then add that to a port, and then now we have our first port, and then we loop over all those ports. So if the next port in the loop is already taken, we're not going to go ahead and move further with that. We're going to go to the next one, and that's what inet check established does. It's the unique check on your ports, like what sockets can we allow you to open and use. And this is what it looks like in code. This is just a small snippet of it, and this is exactly what we're going to be focusing on. So to kick things off, my assumption was that with this hashing algorithm, as if you guys aren't familiar, when it comes to hashing, sometimes they can be prone to collisions. So my initial assumption for this problem was, well, one of the things that we could try to investigate is, are we starting off at the same offset each and every single time? And the theory is, if we are, then if we're also hitting the worst case scenario in a linear loop, then we're always going to hit it each and every single time we make a connection. Purely based off of how this hash is generated, which is generated through the what's called the tuple for a TCP connection. In this case, it's the source IP address, destination IP address, and then the destination port IP address. So it takes these three information, and then it generates a hash based off that, and then that's where and the only independent variable in this tuple is our port, and this is how it determines whether or not you guys are making a connection to the exact same connection at all, because it's comparing against all four of these fields of this tuple. But in our case, we're trying to pick a port, a local source port, and that is our independent variable. Circling back around, we're trying to see if this hash is good or bad. And my assumption isn't that far off base here. Looking through the Linux source code, I like to do what I call Git archaeology, and that is to go through the years of the various Git commits and try to see what was going on for these particular functions. And back in 2011, my assumption wasn't very far off. MD5 hashing, surprise, we learned quite a long time ago that it is very insecure and is very prone to collisions. And then looking at that code, and I don't have any of it available right now, but when we look at the code from that time, all we were doing was just checking that that 3 tuple as opposed to the full 4 tuple, and it was consistently generating that MD5 hash. And so my assumption wasn't far off base. Obviously, MD5 isn't good. It's also slow, so they decided to switch to another algorithm called SIP hash a little bit later on. But the really interesting thing is what happens in 2021 is that some researchers found out that they could fingerprint user devices based off of the next picked port, which further shows that I'm still not far off base with this, because it means that it's very predictable to fingerprint your users based off what the next port they're going to connect to you with. So in light of that research, they decided to add in what's called a perturb table. It's just a fancy way of saying it's a table of random data that we're now going to introduce into the equation to further to make it even more difficult for these to be predictably makes them less predictable. I don't know where I was going to go with that. Anyway, so in 20, but what's interesting is that even that wasn't good enough. So part of the so another aspect of how the hashing works is they take what's known as a salt, and this kind of is generated at the boot time, and then based off that salt generates that hash, right? So even if that salt's going to change per boot, but it doesn't change often. So what they decided to do now is they added 10 seconds to that. So every 10 seconds, it's resalting this hash. So that way, there's even less prediction. So in order to prove that this assumption was either correct or wrong, we needed to run some performance benchmarks on that, and the way to do that was to measure the actual latencies, or to do that we actually measured what port is picked at the time of at the this is to calculate the picked port, the initially picked port, so we can prove that this port is always going to be different, right? And the way I had to do this was because of the way the code isn't created as functions, I had to actually inject this trace into the call path specifically at a specific offset and actually read the registers of it. So this is the assembly part, in case you guys didn't realize already. So the challenge here was, in order to get to this point, I just opened up what's called GDB, GNU Debugger. I ran my kernel, put a breakpoint at the function, and then when I hit that breakpoint, I was able to get all the offsets and figure out where I need to insert my specific hash. And then obviously once you decompile the kernel at that point, you know exactly where to go. So once again, I'm creating a probe or a trace point using a tool called BPF trace at exactly this offset, 22.3, and then I'm reading the register R14, which contains our initial port that we picked before the loop starts looping, and then I added that port to a histogram where the port is added into buckets of 10,000. So if your port is 900, then it's going to be in the 10,000 bucket, right? So it just operates like that. And I do it for the entire range of 9024 through 6535. 65,535. I don't know about you, but I mean, randomness works. This proves to me that everything is working exactly as it should. It is very, very distributed and very, very even. So what this shows is, if we were expecting any sort of bias, any one of these, we'd expect to see these lines go even further. Now, the reason why these numbers don't exactly add up to our 56 our 50,000 count or our port range is because I'm doing this again with a tool called work that tries to maintain these connections over 30 seconds. So we can see that over 30 seconds, each time I try to pick a new port, it was really, really good. So this is that my assumption is now determined to be invalid. It's not that. So let's actually look at what's actually happening within this loop. So once we pick a port, what do we do next? Well, we need to determine whether or not this port is unique. Or I should say this tuple is unique, and we do that through the inet check established. So if you recall from the flame graph earlier, this is that function that takes up a insignificant portion of the flame graph. And if I didn't explain the flame graph properly, the bars represent samples, not time. But you can kind of see that more samples equals longer something took, right? So in our case, the inet hash connect, when we looked at it, went all the way across, but then we can see that just above that, that's when inet check established starts doing its samples, and also takes up a significant amount of time. But through measurement, we found out that this actually is not impacting this is not impacting as we thought, because I was doing all this test within a virtual machine. This virtual machine was not connecting out anywhere. So there's nothing to compare against. There's no sockets to compare against. So effectively, when I looked at this, it was just very negligible. This was not impacting the performance of making the connect syscall. Do keep in mind that as a system scales, as you grow, obviously the search will become longer. So this is going to be another pain point later down the road for us, but as of right now, it's perfectly fine. And as you can see from the flame graph from earlier, that was definitely the case in a production system where we saw a lot of impact within this function. We have another great article, the quantum state of a TCP port, that is worth a look. It gets crazy when it comes to that. So if it's not that, then what is it? We need to look at the actual entire loop in general, because this is basically the gist of the entire function. If we look at, again, this is just a snippet, but the entire function below this point is after a port's already been picked. So if we know that the interlooping is okay, and we know that we're always starting off at an offset, different offset each time, then it has to be the loop. So how does this loop actually work? So the interesting thing is it splits your ports in half, your ephemeral port range in half. And in our case, whenever we open up a new connect, it starts at an even port. This is very important. It starts at an even port, and this is only because our port range starts as an even number. Okay, so the way this works is on a system where we're only allowed to open up 8 seconds or 8 sockets or 8 connections. We start off with socket 0, and we start off with offset 0. So randomly in this test, the offset was picked 0. Okay, great, we made the connection. Next socket. So in this case, gray means it's already taken, but now offset's saying, okay, we randomly picked number 4. Okay, that's currently not taken because it's green, so go ahead, take it. So what's interesting is by the time we get to the third socket, is that the randomization decided to start off at 4 again, but this time 4 is already taken. So it needs to find another port that isn't taken and go ahead and take that. In this case, offset jumped by 2 to 6. So 6 is an even port at this stage, so it goes ahead and picks 6. Great. And then for the 4 socket, same thing, except it starts off at 0 and then just bumps to 2. Great, we're all happy, right? 5th socket. Things get weird. We randomly pick 4 again. Weird, right? We're starting over again on all of our even ports. Well, that's taken, move to 6. That's taken, move to 0. Move to 2. All these are taken. So what happens next? Offset decides to up by 1, make it odd, and then we start off at odd number. So pick 5, golden. Same thing for the next socket, except this time we start off at 0, goes through everything. 1 is perfectly fine, so increment by 1, that's our port. Yada, yada, yada. Socket 8. So in this case, it starts off at 0, goes to 2, 4, 6, done. Increments by 1, 1 is taken, and then now it goes to 3 and picks another odd port. And now we have all of our ports taken. So we can kind of see the pattern here happening already, right? For each time we open up a new connection, we are looping through half of the port range first before we get to the next half of the port range. And it results in something like this. So we ran a different synthetic test this time. Instead of trying to maintain connections over time, here I'm just saying open up as many ports as possible. Use up as many as we possibly can. And because of the 4-tuple, this is the only amount that we're able to open, which is the 56, 512. This is the maximum amount of connections that we can open up at any given time for one source IP address. Green is even ports. Red is odd ports. This is crazy. It took roughly 2 minutes to exhaust our entire port range. Now, the thing I left out earlier is that Cloudflare wants to exhaust our port range, right? We want to establish connections as fast as possible. We want to load balance them as fast as possible once we reach resource exhaustion. But 2 minutes to get there? Users aren't going to wait that long. We don't want that. But the question is, why do we have the split? And the short and the funny answer is that Google just has a lot of services. So if you actually go through the patches in the kernel, you'll find out, like, at some point, you find out that Google has a lot of services that they open up and they pick a bind port for, but they also have a lot of workloads that do connects too. So they have this split up to make it so that your connects are fast, but also your services are fast at finding a port. But here's the interesting thing, right? The arrow's pointing at an odd number. So it's the opposite for bind cases, where for connect cases, we're going all the even ports. Well, for bind cases, they're going through all the odd ports first. And this is where we get that speed up between the two when we have the split. And for those that are not familiar with how servers work, this is a server in a nutshell. Just open up a bind socket, maybe do a listen at some point, do accept, send data back, receive data, yada, yada, yada. But this is just the gist of it. So our conclusion, exhausting half the port range is very, very fast. Port looping is definitely our problem, and this is further evidenced by a previous attempt in the Linux kernel for someone to patch it out. Not great. Now, at this point, some of you might be wondering, are my services having this problem? So I offered another BPF trace script here, which hooks into the inet hash connect function at the point it returns. And then when it returns, if it's 0, that means it's successful. This is going to execute. And then you can go ahead and grab the actual port that was eventually picked. And then I created a little histogram here that will show you the counts for each binary under their respective C group and then whether or not, how many times that binary has gone over the port limit, the halfway point. And this is and this only works for even ports. If your low port range was an odd number, you need to switch this and around to 0, because when I'm doing it as 1 right here, I'm saying, like, if this is even number, ignore it. Only count it if it's an odd number, because that's exactly what we want. No, now I'm thinking if I have that wrong. Being up here in presentations are crazy. Anyway, if it was an even number, it'd be 0. So you're incrementing nothing. So that's the gist of it. All right. So this could be extrapolated to a Prometheus vector, in which case you can measure the rate of your binaries over time with this BPF trace. And Cloudflare offers a tool called Prometheus Exporter for eBPF metrics, in which case you can implement your own eBPF metrics to export out to Prometheus and get this data that you like to from within the kernel. What do we do? We thought of 6 possible ways we can deal with this. Now, the 6th one was added recently And I'll go more into that later. But the gist of it is we're gonna talk a little bit about load balancing. We can introduce another syscall. We can use user space. We can have user space do this for us, or we can leverage some kernel features as of version 6.3. What we ended up doing, and then what is coming in Linux 6.8, which that happened this year. We're now at 6.12, so we'll talk about that in a minute. So number one, load balance egress unicast connections over 2 or more IP addresses. So we already do this. And again, the problem is we don't want to have more IP addresses. Now, in an IPv6 case, this is a perfectly valid strategy, right? We saw it before where we only had three IPv4 addresses and how fast that was, right? And that's because when you split the traffic over those 3 IP addresses, they're no longer crossing over that halfway point, and that's why it's fast. So if you have IPv6, you can have those for days, and you can load balance those over multiple days, and you'll be perfectly fine. But again, reality is most people still use IPv4 at the present time, so we need to reduce down to 1. So this strategy, not good for us. Now we can introducing another syscall. The problem with this is that it requires actual kernel modification, and the problem with that is you also have to support it. Someone tried to upload this themselves, ultimately didn't make it into the kernel because the solution missed, I think, 1/4 of the ports, which is not great, because that just reduces the amount you could potentially use by 1/4. So it was ultimately rejected, but you can actually do some manipulation here by introducing your own patch. We didn't want to do that. User space is interesting. What you can do instead is you can leverage the randomization of, and it doesn't have to be a great pseudo-random number generator. You can just use some random number generator and actually pick the ports yourself. So instead of having the kernel pick the ports for you, you can have user space pick the ports, and you can just keep track of those connections. And this is some sample code, and I did verify yesterday that it does work if you implement the helper functions. But the problem with this approach is that it introduces syscall overhead. So another performance problem with Linux or Windows or Mac, what have you, is every single time you connect out to, or you try to do something within the kernel and perform a syscall, you're reducing overhead. And the more overhead you introduce, the slower your application becomes. So in this case, while it's perfectly fine to bind this way, the problem is you're introducing more syscalls and potentially more slowdown. The other issue is that this is only really good up to 70 or 80% of the port range, and we'll find out why later. But the gist of it is that once you start exhausting your ports, this thing gets slower and slower and slower. So it's not, it works great, it's fast, but it's not good enough, right? So at some point in Linux, in 6.3, a new socket option was introduced called IP local port range. So this socket option allows us to partition port ranges per connection. So we can say that connection 1 uses 0 through 10. Connection 2 uses 10 through 20, right? So you just kind of go like that. And that's what partitioning is with these ports, and this socket option allows that. But when you try it with a partition of 5,000 ports, you can still see that the problem's still there. So even though we were able to open up 5,000 connections in 1 second, a little over 1 second, it's not great. It's still slow. We want to eliminate that slowness. If you reduce that window down to 1,000, obviously things speed up, right? So now we're in a case where we're able to, in less than even this is still like nearly an order of magnitude better, right? Of performance increase by switching down from 5,000 to 1,000 window. The loop problem's still there. You can still see it barely between the green and the red, but it's still there. Now the other interesting thing about this solution is that it allows you to overlap port ranges per connection, and that's going to be very important for our actual solution. So In user space, we went from 2.1 minutes down to 1.8 seconds for opening up 5,000 connections. Not 5,000, 56,000 connections, and the results are staggering. Multiple orders of magnitude better performance. Using a combination of randomly picking an offset for the port range and then overlapping with IP local port range windows. Crazy. The reason why this works is that, recall earlier, if your low port is odd, it starts looping at odd. If it's even, it starts looping at even. So the trick to this is that it starts at odd or even and it randomly picks between the two, and you get this massive, 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 massive performance improvement. So a little bit more about how that works, right? So in our case, our system is 9024 as our low port, and our high port is 65,535. So it's represented by these blocks. We're going to create a window, 0 through 500. So we're going to create a 500 port window. We're going to offset that by some random number, and we're going to offset it so that it still neatly fits within our entire port range, because we don't want it to go over. That makes no sense. It's just going to wrap around. It's not great, right? So what we want to do is we want to randomly offset this window within this range, and we do that through by creating the local port, setting the socket option, but also offsetting the low port to be that random number. And again, overlap is okay. So recall earlier when I said that we had in the bind case in user space, there could be a time where you randomly pick a port that's already picked, and the next one's already picked, and the next one's already picked, yada yada yada. Same thing here, but it's okay because we now have a range to work with. So you're guaranteed to still get some port, not all the time, because it's possible that ranges can overlap still, right? But it doesn't happen as much. And we'll find out more about that in a little bit. But some reattempts may be necessary, but it's all depending on your implementation of it. So some benchmarks. So in the 500 window case, this is with only 500 connections that we make at any given within a 500 connection window, we get our 1.8 seconds. As you can see, as you go up in window size, you're now getting diminishing returns. Now, 2 seconds is still crazy good, right? And in our case, we now introduce these black dots, which are the error ports, right? So we can also see that as we up our window, error rates increase. And this, again, when I talked about earlier, once you get to 70-80% of your ports taken up, you start introducing error where you can no longer make a connection at that port. But for our case, that's still pretty good. That's basically what we want. We want this to go and fail as fast as possible. We don't want to wait 2 minutes. We just want it to go and fail as fast as possible. Again, 5,000 window, error rate increases. 10,000 window, error rate really increases. Now, the interesting thing about this approach is that really what you want is you want this little sweet spot of you want just enough of a window to have to make your loop run quick enough, right? This 500 window, but you also don't want it small enough to where you're in the user case where you're just picking you're picking your own port in the bind case. So if you only had a window size of 1, it's no different than doing the user space solution of just picking a port at random and then hoping it works, right? And do retries. If it's too big, you run into the same problem that we had before, where you're exhausting your entire port range and it's taking 2 minutes. So there's a sweet spot here with these window sizes, and this is evidence of that. So in summary, this approach is really good, but the question is, can we do better? And the funny story is, yes, we can, and that's specifically because after I gave this talk at Linux Plumbers last year, the maintainer for the Linux, the networking subsystem, decided to implement a patch leveraging IP local port range as the trigger to enable this, such that when you use the kernel, you no longer need to calculate your own offset range. It automatically does that for you. Better, there's no more errors here, because previously in the kernel implementation, it was guaranteed to always give you a port, always to give you a connection for your max range. And it's no different here. The only difference is now we're allowing it to use well, instead of looping over half and then going through the other half, we're allowing it to just go ahead and go through the entire thing very linearly. And the performance is still crazy better. Now, again, these numbers aren't super great at this point. Well, I mean, they are. I mean, 1.6 is a lot better than 1.8, but the difference here is that as kernel versions increase, bugs are fixed, other performance problems are fixed, and eventually you can get into a case where things just get faster and faster and faster, which is exactly what we want. So now we use this. I basically just said this slide in the last one, but the gist of it is guaranteed to find a port. Great. Here's the patch that actually introduces that, and you can follow that link there. This is how it's actually implemented. So before we saw that we were calculating our window sizes and we were offsetting them, but now we no longer need to do that. So this is the full implementation here. You just set your IP bind address no port, you give it your port range, boom, you are done. And in this case, we gave it the entire system. So what's funny about this is that it still allows you to partition your ports up, but it only works and is enabled for that specific port range, for that specific connect that you're opening up. So what's really interesting here is that if you want to get the full benefits of this for your entire port range, you literally have to set this socket option to your entire port range, which is kind of funny, but that's just the way it works to enable this feature. Oh. Now, some of you that use UDP might be wondering, well, what about UDP? So I was asked this question again the last time I gave this presentation at Plumbers, and I didn't have a good answer for that, mostly because we didn't care at the time, and also because it's a completely different algorithm. It's really hard to compare TCP and UDP in this case, apples to apples, just because for the fact that UDP is considered stateless, or if not really truly stateless, it's more considered like it's socketless.
Can you define UDP for us?
No. I was worried someone was going to ask that, but the problem is like I know the acronyms, I know what they do, I don't know what they are. It's just a weird quirk of mine. Anyway, UDP is a different protocol from TCP. The way it works is it allows you to send information out into the void, and that's it.
Is it not unicast?
It can be multicast, unicast. Same thing with TCP. Yep. So the thing about UDP is that it's a very different algorithm. So you can't compare them apples to apples, but I tried my best with the benchmark to set up a very similar situation. But the main difference here is that UDP is very fast. It runs through the entire port range just like TCP, but by default it goes through the entire range without having to go this even an odd split. Furthermore, UDP doesn't really keep track of sockets at the moment. There's work being done right now to make that happen, but right now there's not really any socket tracking, which means that there's even less that this loop is doing. And the other thing that this loop is doing is that it's picking a random number and then it's looping through multiples of that number over and over and over and over again. Eventually, it leverages an integer overflow, and it will get back to the exact number that it was before. And in that moment, if all other numbers selected between that point were already taken, it'll increment by one and do it again, right? So it's very similar to how TCP works in that regard, except for the fact that it's leveraging integer overflow, which normally in programming you wouldn't really want to do. That's just going to ask for bugs. We talked a lot about, if it wasn't obvious before, we talked a lot about latency, but nothing about throughput. If you recall earlier in our benchmark here, for one IPv4 address, we were trying to maintain 70,000 connections over 30 seconds. Okay? The problem is that work will open and close those. Open and close, open and close, open and close. So unlike my other benchmarks where I'm trying to explicitly keep sockets open, work will open and close, open and close, open and close, right? It just sends like basic HTTP requests, things like that. But now we have to talk about the TCP state machine. I'm not going to go into details about this, but the gist of what's happening here and the reason why we can't get more throughput with our chart and within those 30 seconds is because whenever a connection gets closed from our end, remember, we're making egress connections. Whenever we ourselves close that connection, eventually we enter into what's called a time wait TCP state. And this is right before the connection actually closes. And the reason for this state is that you want to ensure that whatever packets are in flight, because again, this is all asynchronous. So whatever packets are in flight between the machines, this allows your server, their server, etc., to be able to handle whatever happens while the connection's in this state. Now, in normal cases, you yourself as the application developer aren't going to be able to do anything with this, but it allows the kernel to tell the server, like, hey, look, we closed it. We're going to send you that pack and let you know that we closed it, things like that. So go ahead and close it on your end too. And that's the whole point of time wait. But time waits a long time. So using a tool called SS, you're able to peer into all the open connections you have on your system. So in this little case right here, I'm trying to open up 11 connections. Sorry, I had 11 connections, but I changed it to 10. Here we're trying to open up 10 connections, and we get all to the same destination, but we can see that whenever I close the connection, it went into time wait, and it takes about a minute to close. Now, I tried doing very extensive research last night. These slides were very recent, so I was trying to figure this out last night, like what we can do about this. But unfortunately, I couldn't come up with anything in time. But the gist of it is this is what those black dots are in this benchmark, right? So when we have the window case, where now we have an overlap of where we're now trying to make connections on already previously opened ports, those black dots are the time wait. So in this case, if we now you could use like a socket option called SO reuse port. I won't get into exactly the details and nitty-gritty of it, but essentially in that case you're able to reestablish connections on connections that are in time wait. But in our case, we're kind of held to that. So we're working on it. I don't have any benchmarks or anything fancy to show you right now, just for the fact that this is still evolving. We're still working on this. Right now, time wait is working on a second resolution where we could have it in milliseconds. We are trying to propose a solution where you can make this tunable, so that way you can say like, hey, we know we're going to close this connection really fast. Let us just close it so we can open up that port to allow something else to get through there. And that's kind of where we're at on that. You can look at this patch. It was first proposed in August, and it's still going through the development lifecycle at the moment. So we're working on it. So takeaways: networking's hard. Performance is hard. If there's nothing else that you learn from this case study, is that there is a lot that goes into performance measuring. We didn't even scratch the surface on anything else within the TCP stack. We were focusing on literally picking a port. Let that sink in. Just picking a port. Wild. So networking, there's a lot going on. There could be a lot more improvements. Come work with us. Come work at Cloudflare. Come work at at any other tech company, because we're working around the clock trying to solve these problems for you, the customers. The situation is always evolving. Every single time new code is added, more potential for attacks, more potential for performance bottlenecks. So we need people to come in and really go in there, measure, tune, and tweak. And please upgrade your kernels. Like, in August, I gave a presentation about an exploit I found within the Linux kernel and fixed. But you can't get those fixes without updating your kernel. So if it's not for exploits, at least go for performance. I mean, I feel like you should upgrade for exploits specifically, but you know what? If nothing else, go for performance, right? Zoom. Go fast. And Uncle Sam, he wants you. So, takeaways. Again, I thought so the problem with PDF, I meant to hide that slide, but PDF exported out. So, all right, questions.
Oh, how long did it take you? Like, how much time did you spend on this investigation?
Yeah. I was asked how long did I spend on this investigation? A long time. So, in between all the testing, all the benchmarking, and all the time wait situations I ran into, because every single time I tried to perform a test, I had to wait a minute before I could do the next one, right? So, that or I switch IP addresses and it'd be perfectly fine. But then that would skew the results a little bit because now we have open up ports and things like that. Beside the point, it took a long time. We had to investigate how cache worked. I had to investigate how the TCP worked in this case. I had to investigate obviously whether or not we're starting off the same offset or not. And all this took time, and we knew pretty early on that it was probably the loop, right? But we didn't know how that actually impacted our caching service until we actually went in there and investigated, and that's what took the longest time was all the measuring, all the testing, all the retesting, making sure that this presentation is accurate, all this stuff over and over and over again, to ensure that we're on the right track and our solution actually is the solution we want to go with, which eventually all that hard work paid off. Like I said, the Linux kernel maintainer for the networking subsystem, probably enough people complained at him based off this presentation that he finally implemented a patch that fixed the problem. And I have a blog post here where this basically the whole presentation is distilled in that, and some code that generated these charts. Hopefully that answers your question. Anyone else? I must be really good because this stuff's crazy. All right. Well, I guess we're done